That's it.
Okay. The link and other facilities for the online presentation seems to be okay. It is a really great pleasure for all of us to have here Professor Merdji for the noticeable talk on new type of matrix deformations and applications to biharmonic maps. Professor Merdji, do welcome to your presentation, please.
Thank you, sir. So before I start, I would like to say to the committee, thank you so much for giving us this opportunity. And now I will present my work, which is new types of matrix deformations and applications to biharmonic maps. And it's my work, me and my supervisor, Professor Ahmed Mohamed Sharif, and we both are from Mascara University of Algeria. So the summary contains, first of all, an introduction where I will define the harmonic and biharmonic maps. Then I will go to the deformations of the matrix. And finally, we will see all of us the applications to biharmonic maps. So an introduction. So we have two Riemannian manifolds, M equipped with the metric G and N equipped with the metric H. And the energy functional of a map varphi, a differential map varphi, is defined by the equation number 1, which is equal to 1/2 integral on M, the squared norm of the differential of the map varphi Vg, where this is the Hilbert-Schmidt norm of the differential of the map varphi, and Vg is the volume element on the manifold M. So a map is called harmonic if it is a critical point of the energy functional, that is, if it is a solution of the Euler-Lagrange equation associated to 1, which means that a map is harmonic if it satisfies this equation, which is number 2. That means that the tension field of the map varphi, which is given by the trace of nabla d varphi, is equal to 0. It vanishes, where this frame is an orthonormal frame on the manifold M equipped with the metric G. Nabla M is the Levi-Civita connection of M equipped with G, and nabla varphi denote the pullback connection on the inverse tangent bundle of the manifold N. So harmonic maps are solutions of a second-order nonlinear elliptic system, and they play a very important role in many branches of mathematics and physics, where they may serve as a model for liquid crystal. One can refer to these references for background on harmonic maps. A natural generalization of harmonic maps is given by integrating the square of the norm of the tension field. More precisely, the B energy functional of a differential map varphi is defined by this equation. E2 applied to varphi is equal to 1/2 the integral of on M of the squared norm of the tension field of varphi Vg. So now we go to biharmonicity of any differential map. So a map varphi is called biharmonic if it is a critical point of the B energy functional, that is, if it is a solution of the Euler-Lagrange equation associated to 3. So we have the B tension field of varphi is given by this equation. It is equal to minus the trace of the curvature tensor of the manifold N applied to tau varphi, d varphi, minus the trace of nabla varphi squared applied to tau varphi. So a map is biharmonic if this B tension field, vector field, is equal to 0. So clearly, harmonic maps are biharmonic. And then G.Y.G. Yang proved that if M is compact without boundary and the sectional curvature of N is negative, then any biharmonic map is harmonic. So it is interesting to construct biharmonic non-harmonic maps, and we refer the reader to these references for other examples and different approaches to their construction. Now we move to deformations of matrix. So we have M is a Riemannian manifold equipped with Riemannian metric G, and F is a smooth function on N, such that G tilde is equivalent to G minus dF. Tensorial product dF is a Riemannian metric on N. we have G tilde applied to X comma Y is equal to G applied to X comma Y minus X applied to F, Y applied to F, where X and Y are vector fields on the manifold M. So note that if M is a connected M-dimensional manifold, a continuous function F defined from M to R is called proper if the inverse image of K by the function F is compact for every compact K in M. A Riemannian manifold M is complete if and only if there exists a proper smooth function F such that this formula is this deformation metric, which is given by G minus dF tensorial product dF, is positive definite. In the seminal work, we obtain the following results. So the first theorem, we have always M is a Riemannian manifold and F is a smooth function on M. If the squared norm of the gradient of F is equal, which is equal to G applied to gradient F is smaller than 1 on M, where the gradient F is the gradient vector of F with respect to the metric G, then the deformation metric G tilde is a Riemannian metric on M. Moreover, if nabla tilde denotes the Levi-Civita connection of M equipped with the metric G tilde, we have the covariant derivative on the manifold M equipped with G tilde is given by this equation, where nabla is the Levi-Civita connection of M equipped with G, and Hess F is the Hessian of F with respect to the metric G. Now we consider the curvature tensor R tilde, respectively the Ricci tensor Ricci tilde of M equipped with G tilde, and then writing R for the curvature tensor, respectively Ricci for the Ricci tensor of M equipped with G. So we have the following results. Theorem number 2. So M equipped with G is a Riemannian manifold and F is a smooth function on M, such that the norm of the gradient of F is smaller than 1 on the manifold M. For every vector field X, Y, Z on the manifold M, we have that the tensor curvature R tilde on the manifold M is given by this equation number 7. And as you can see, there is a relationship with the tensor curvature R tilde and the tensor curvature R. And to obtain this result, we have a simple calculation. We use the property of the definition of the tensor curvature and the definition of the deformation metric that we have mentioned before. So we have the theorem number 3. M equipped with G is a Riemannian manifold and F is always a smooth function on M, such that the norm of the gradient of F is between 0 and 1 on M. Then the Ricci tensor of M equipped with G tilde is given by this equation. And the same thing, the Ricci tensor tilde applied to X has a relationship with the Ricci tensor applied to X for all X vector field in the manifold M. So the main idea of the proof of the previous theorem or the above theorem is to compute the Ricci tensor of MG tilde is that we need to compute this the following equation, and we use two orthonormal frame. We have this one and this one with some characteristics, and by using theorem number 2, we obtain the above result. So it's so simple. Now we move to the last section. This is the most important section of our work. Here we will consider the effects of a deformation of the codomain metric as regards harmonic and biharmonic mappings, and we will try to construct new examples of biharmonic, non-harmonic maps. So we have theorem number 4. We have var phi is a map between the manifold M equipped with the metric G and N equipped with the metric H. So here we assume that this map is harmonic. And then we give the deformation metric of the codomain H tilde, which is equal to H minus df tensorial product df. And f is a smooth function on the manifold n, such that the squared norm of the gradient of f, which is equal to h applied to gradient f, comma, gradient f, and equal to 1/2. So we have, if the function Laplacian of f circle var phi is a non-null constant on M, then the map, the new map, which is given by, which is defined from the manifold M equipped with G to N equipped with the new metric H tilde, is proper biharmonic if and only if the gradient vector of f is a Jacobi field along var phi, which means that the gradient of f circle var phi is an element of the kernel of the Jacobi operator corresponding to var phi. And what we mean by proper biharmonic map is that this map is biharmonic, non-harmonic. So we have as an example a map defined from a manifold M, which is equal to Rn, and Rn is equipped with the usual metric, to the manifold N, and the manifold N is equal to the n-dimensional hyperbolic space. And this is how we construct the construction of this map. And we have the function f applied to y1 until yn, which is equal to the root of 2/4 yn squared. So a straightforward calculation shows that, so after some computation, we find that the squared norm of the gradient of f is equal to 1/2, and the Laplacian of f circle var phi is equal to n minus 1 over the root of the squared root of 2. And then the gradient of f circle var phi is equal to this vector field. So this vector field, all the components vanish except the last component. It's different from 0. And the Jacobi operator of corresponding to var phi of gradient of f circle var phi is equal to 0. Thus, with respect to Riemannian metric, we find the deformation metric, which is given by h tilde equal to h minus df tensorial product df, and equal to this. So as you can see, this map is biharmonic, non-harmonic, and here we have the tension field of this. It is obvious that the tension field of this map is not null, because we have the last component is equal to minus the root, the square root of n minus 1 over xn squared plus 1. So this application is biharmonic, non-harmonic. We have as a remark, var phi, this application or this map var phi is harmonic, and h tilde is equal to h minus df tensorial product df. F is a smooth function, this time on n, such that the gradient, the norm of the gradient of f is smaller than 1. Then the map, the new map, which is defined from the manifold M equipped with G to N equipped with the metric H tilde, is harmonic if and only if f circle var phi is harmonic on the manifold M equipped with G. So for finishing, we have corollary. We have M equipped with G is a Riemannian manifold, and let f is a smooth function on M, such that the norm of the gradient of f is equal to 1/2, and the Laplacian of f is equal to a constant k. Then the identity map from M equipped with G to M equipped with G tilde is biharmonic if and only if it is harmonic. So that's it. These are our references. and thank you for your attention.
Okay, we thank to Professor Merdji for her nice presentation. If there is any question or comment, please use the question and answer button. Let me check. Okay, there seems no question or comment. So we thank again to Professor Merdji. Stop your screen sharing, please.